So, my name is Andrea Luis. Today I will present about the surface photometry of BCGs. I choose to talk about this because the first that I did, I sensed that um, I can't explain too much about the article. So I'll give a hint about what I do in the lab. Um, and and also a little bit about the methodology of the last article that I present. So um, I will talk this about the introduction. That I remind you that I work with BCGs. That is the brightest cluster galaxy. Um, one example is the the image here. It's about the Abel cluster, I think. I don't know which one. Sorry. But superficial photometry is a technique for analyzing the distribution of light over the entire physical extent of the object, in my case, the BCG. So, one way to investigate the distribution of a galaxy surface brightness is to characterize the shape of the radial brightness profile. That is how the average surface brightness of the galaxy varies depending on the radial distance to its core. Okay. And among many other applications, this technique assists in the morphological classification of the object. Science different structure components have systematically different radial brightness profiles. Also, understanding and identify the presence of structures and the characterization of physical properties of these bodies. Um, in my work, I use a routine called GALFIT that fit a radial distribution model on these galaxies. So the routine GALFIT adjusts radial brightness functions for large bodies or point sources. In this case, or galaxies or stars, based on user supply surface brightness distribution models. So GALFIT um, needs a model that I'll talk in the next slide, in the number of free parameters. I give them a guess about these parameters, and the routine do a model with the convergence of these values. So GALFIT determines the values of those parameters that best describe the object. And among these parameters that characterize a galaxy brightness distributions are I need to give them the position of the center of the galaxy in the image, the apparent magnitude of the object, uh, the apparent physical extent, or the effective radius, the degree of apparent flatness, E, the orientation of its major axis, the position angle, and the function that that has the form of for radial dependence on the surface brightness of the object. In the case, the gas from a function as an analytical radial brightness profiles uh, are functions that describe how the surface brightness of the galaxy behaves from the center to the edge. So there are several functions that can describe the galaxies and point sources. I use most the SAR6 law that is about this equation here, where sigma r is the surface brightness of the galaxy at a projected distance r from its center. Re is the radius that contain 50% of the integrated flow of the galaxy, called effective radius. Sigma E is the surface brightness at a radial distance equal to the effective radius. called effective brightness of the object, and n is called the Sersky index and has the function of describing the curvature of the profile. The Bn is a function of the Sersky index and is given by this equation here. The typical n value for elliptical galaxies and spiral galaxies cups is close to 4. So that is another loss, let's say this, but I don't use that too much. Okay, I don't know the equations also. I don't look, sorry. So there is Valkuler's law is identical to Sersky's law with any n equal 4. Exponential law, generally used to describe spiral disks and lenticular galaxies, and equivalent to a Sersky law with n equal 1. I use this function also to describe this function together with Sersky's law describes one type of galaxy that I work on too. The Gaussian function used to model unresolved sources. Ferrer functions and empirical King functions used to represent globular star clusters. So, in my work, I already said that I use the Sersky's law. So, before I I start the routine GALFIT, I need to give them some images for him to work on. So I need to give the image of the galaxy to be adjusted, a map of useful pixels in the image, which we call mask image, a map with the statistical weights of each pixel in the image, which we call sigma image, a model for the point spread function that characterizes the observation, which we call PSF mesh. E So this work frankly use a large sample of objects. So I developed an algorithm in Python to obtain and organize this input data for each BCG. So this algorithm, um, ele, the algorithm finds the coordinates of each BCG um, in a data. So the routine goes to a database. In my work, I use the SDDS database. So he made the downloads of their respective frames together with a file that contains a mapping.
2 minutes.
Okay, a mapping of the characteristic of the PCF along that frame. After that, the algorithm determines the location of BCG on that frame, not in the sky as a whole, but only that frame, and identifies the pixels associated with it and the pixels contaminated by peripheral sources. In this case, we use to locate these objects and the creation a mask to, let's say, take off this peripheral source using the extractor routine. This extractor identifies in an astronomical image the different individual sources and which pixels are dominated by the brightness of each one. In addition, this extractor estimates important parameters for each source, such as the axial ratios, the position angle of the major axis, its apparent magnitude, and its tensions. In resume, I use the values that this extractor finds about the BCGs as a guess to GALFIT for him to create the model. After this, this extractor applied to each BCG algorithm creates a cutout center on the BCG for further analysis. And it determines two masks, the mask A, which identifies the location of intruding sources, and mask B, which identifies the pixels dominated by the brightness of BCG. Uh, until now, I only read the text, but now I will present some images for you better understanding. The first one are the frame image. These images are the that I downloaded from the database. As you see, it's a huge image for to work on. So I need that's the why, because I need to do the cutout image. Okay, because I don't know which one of these objects are the BCG. So I apply extractor for him to find the BCG, then cut out the image for better computational processing. So after the cutout, he do this image. It's about 500 pixels. The light of there is no image greater than 500 pixels. I think it's that the median value. So I give this image and this extractor the mask A that take off the contaminated sources, and mask B to find the BCG. Okay, so only the pixels that apply to the light of BCG. In Sigma image, it's a weighted of the values of each pixels in the sky. Okay. So the last part, after I give all those guesses to GALFIT for one BCG, all those images, the GALFIT give me two outputs. The first one are a list with all values, the convergence values of the best model that he described the object, and in this frame with three images. The first one is the original image, that the cutout image. The second one is the model that he creates. And the third one is the residual image. And I use this image, the residual one, to understand the galaxy that like to find multiple nuclei, or it has some uh, tidal, some like something happens on the galaxy, the fusion, or um, there is an envelope on of the light. In this case, I don't know if looks that you can see because the image is too bad. There is light, that too much light on one side of the galaxy that can say to us it's the galaxy past some phase of fusion with other objects, and after that I start to understand all the other objects and give the results that the last article that I talk about the last article. That's it. Thank you.
Okay, thank you. Questions? Perguntas?